Good morning, you all. Today we will discuss a new topic in VLSI technology, that is assembly and packaging. In my last few lectures, we have discussed on how the ICs, in particular VLSI chips, are fabricated. Starting from the wafer level, how different layers are formed to have the complete chips, and we also discussed the modern innovations and techniques in VLSI processes, including bipolar processes, CMOS process, and at the end we have discussed on BiCMOS processes. After the chips have been fabricated, next job is to test the correct chips and to separate the chips from the wafer and to assemble them in a package to protect the chips from environment and other means. Today's lecture is on these particular problems of assembly and packaging of VLSI chip. The packaging of VLSI chip is a broad subject that ranges from pre-assembly wafer preparation to fabrication technologies for the pack. Progress in the wafer fabrication process also leads to challenges in assembly techniques. For example, the introduction of new metallization material to reduce space-induced migration requires a corresponding breakthrough in interconnection techniques. The VLSI package design must meet various demands from the package chip testing, handling systems, and also next level packaging. Generally, a high density VLSI package that contains a comparatively larger chip requires a smaller external terminal spacings. This jeopardizes the post packaging processes. Now, I will discuss one by one what are the problems, what are the points we have to consider in detail when we select some packages, what are the various steps in packaging and assembly of VLSI chips. Now, we will see for a package on assembly of VLSI chips, improved packaging techniques has to be evolved, because day by day chip sizes are going to reduce, and because of the improved packages it is now possible that electronic appliances and enhanced electronic appliances are downsizing, at the same time the performance are being enhanced. So that is to be taken care when we are searching for new packages for improved performance of the chips. The logic and microprocessor devices with high I/O terminal numbers, higher speed, and a high power dissipation create additional challenges for packaging technology. Progresses in wafer fabrication process lead to challenges in assembly techniques, including chip bonding and wire bonding. Now, package designers need to achieve larger input output pin counts, a better thermal path, and excellent electrical performance in a smaller package. In present VLSI chips or VLSI chips, microprocessor chips, the number of pin counts are large, input output pin counts are large. So accordingly, the assembly and packaging techniques are getting more and more complicated. Packaging significantly affects the overall cost, performance, and reliability of the packaged chip and the system. Packaging cost is important as it accounts for a considerable portion of the total cost of VLSI packaged chip. packaging cost is likely to be more dominant than the cost of the chip itself. And it has been seen that in a VLSI chip, the more than 50% cost is coming from assembly and packaging area. So we have to evolve certain techniques so that the yield will not be disturbed during packaging, and also the cost is getting low day by day compared, so that we can have a good marketing. All of the packaging issues, including the assembly techniques, will be discussed in this lecture. Now, I'll concentrate on generic assembly sequence for packages. What are the sequence we have to follow for packaging a VLSI chips? The wafers preparation starts with the back grinding process at the end of wafer fabrication process. So you can see first of this sequence is wafer preparation. This wafer preparation means I am talking of finished wafer. That means once the chip has been fabricated and passivation layer has been put, then the complete wafer is coming in the assembly and packaging area of the fab. Now there the first job is wafer preparation, means you have to reduce the thickness of the wafer. The normal wafer size nowadays is 6-inch diameter wafer, and you know for 6-inch diameter wafer the thickness of the wafer is around 650 micron. Now this thick wafer cannot be separated easily into small die or chips. So what we have to do, the first step is to thin the wafer thickness. That means thinning down the wafer thickness is done by back grinding. We have to grind backside so that the thickness of 650 micron is coming down to nearly say 200 micron or 250 micron. So this is the first job of wafer preparation. And after the wafers are thinned down, the next job will be the chip bond. Chip bond means on the wafer you are having large number of chips, nearly of the order of say 10,000 or 20,000 chips are there at the same time. Now your job is to separate these 20,000 pieces. That means after thinning down the wafer thickness, now you have to scribe the wafer so that small pieces of individual chips are coming out. That is known as slicing. So you have to slice the chip using the diamond wheel. Very sophisticated automatic diamond scribers are used nowadays for slicing the wafers. Diamond wheel of blade thickness 25 micron nearly is used, and it rotates in a speed of 20,000 rpm, and it's fully automatic. So the wafer is sliced one row and the next row in this way, and after slicing the wafer using diamond wheel, we separate individual chips from each other. So now in VLSI technology particularly, the slicing portion, that means the diamond wheel, the cutting depth is nearly 90 to 100%, and then you can easily separate out. In earlier days, when chip complexity was not that much and wafer chip size is also not very large, so that time people used to have the cutting using diamond wheel nearly 50 to 60%, and after that they used to break the wafer to get it small, to get the small pieces of the chips. But nowadays the chip size is large, at the same time complexity is high, and wafer thickness is also becoming large day by day because of the use of large diameter wafers. So what they use now, the slicing is nearly 90 to 100%. After that, the whole wafer is pasted on a adhesive tape, is put on a adhesive tape, and then it is sorted. The good chips are sorted and bad chips are rejected like that. So now, if you look into the general assembly sequence for packages, the block diagram shown here, the steps involved in assembly sequence. After the wafer preparation, then you are thinning the wafer by backside grinding, then you are slicing. Your next job will be chip bond. The chip or die, the technical name is die, that has to be fixed on some package. Okay, so that is done by solder preform and polymer adhesive. There are different kinds of chip bonding. I will discuss one by one. Next comes, after chip bonding is over, then comes wire bonding. In a wire bonding, the individual connections of different bond pads are made with the beam lead. The package has got certain posts which are coming up to the outside of the package, which are coming outside of the package. The inner side of the post is used for bonding purpose from bond pad of the wafer to the post. That is done by wire, and that is aluminum wire and gold wire are used normally for wire bonding. First chip bonding, then comes wire bonding. After wire bonding is over, then we encapsulate the chip. That means we cover the chip, and after covering the chip, then we seal the package. See, after covering by top layer of this package, then we seal it, and then it is going for test. After encapsulate, then package seal, then going for test. In some cases, directly after wire bond, we can seal using certain packages, direct sealing without giving the upper cover or encapsulation. And in some cases, after encapsulation, it is directly molded. Some of the chips directly after wire bonding is also molded. So different techniques are available for giving final shape of the chip. At the end, we test the chips whether during packaging some error has introduced or not. During packaging, it always happens some of the wiring is not proper, dry soldering for example may be there, so those chips will not function. We have to reject those chips. So this is the total sequence we have to follow for assembling the chips, for making the package chips. Next, assembly of VLSI chips can be broadly categorized into three sections. One is chip bonding, then is wire bonding, then packaging. So chip bonding, there are three varieties. One is known as solder die bonding, other is known as epoxy die bonding, and the third is eutectic die bonding. Solder bonding is the initial stage of the assembly technique. We use solder die bonding. With evolution of improved die chip bonding technology, gradually we shifted from solder die to epoxy die bonding, and then we switched over to eutectic die bonding. Details of these die bonding and main features will be discussed. Then comes wire bonding. There are four kinds of this wire bonding is mentioned here. One is known as thermocompression bonding. That means here thin wire of gold is bonded with the bond pad to the package lid by using thermocompression techniques. That means we use thermal energy, at the same time we give certain pressure. So that sometimes known as ball and wedge bonder technique. We discussed it. That is the thermocompression technique. In another technique, we use ultrasonic energy for bonding the wire onto the pad. So that is known as ultrasonic wire bonding. In the next is bonding beam lead chips. That means here we do not use any wire, rather than we use beam lead. Directly bond pads of the chip are connected with the beam lead. Some bumps are there, metal bumps, and on the bump we place the chip inverted. The bond pad will be connected to the bumps, and we pressurize it, and there it is bonded. That is known as bonding of beam lead chips. And another category is automatic wire bonding. So here also we use this either aluminum or gold wire of thickness 25 to 40 micron thickness of wire we use for bonding purpose. And after the wire bonding is over, then comes packaging or molding. So in packaging we will discuss the purpose of packaging and types of packages available nowadays in VLSI package assembly techniques. All those points will be discussed. Now first I am switching over to chip bonding. In a chip bonding, this is basically the fixing up the die or chip on to a substrate material, and this substrate material is the base of the package, we can say, and that package may be made of plastic or ceramic coated with some metal film. So now the purpose of the chip bonding is to attach mechanically the chip. Attach means which side? Back side of the chip is attached mechanically to an appropriate medium such as ceramic substrate or paddle of metal lead frame. That is the main purpose of chip bonding. Next, chip bonding provides a thermal path. Very important. Chip bonding provides a thermal path from the chip to the medium, and sometimes allows electrical connection to be made to the back of the chip. That means the chip bonding technique provides a good thermal path from the chip to the outside of the package. Chip bonding technology is determined by selecting among a variety of trade-offs. What are those trade-offs? They are thermal stresses caused by TC mismatch, temperature coefficient of expansion TCE, that is very important, between TC mismatch between the chip and the package materials, power dissipation. Power dissipation means here you need thermal path from the chip to the medium, external medium. Next, electrical capabilities and reliability and cost. These are the various points which have to be considered when we are adopting a certain chip bonding technology. Particularly, the power dissipation and the TC mismatch is very important. If TC is not matched properly, then there is a chance of development of micro cracks inside the chip, and as a result of which the chip will not function after complete packaging, and you have to throw away those chips. As a result, the total yield will be extremely poor. Now comes the chip bonders usually has features such as a good chip sorting function, a pickup and place unit, a chip attach material supply station, and lead frame loader and unloader. Why those features are necessary? Because on a wafer there are large number of chips. Out of those chips, it may be possible that few of the chips will malfunction. So that means before coming to the assembly and package section, that these chips are tested, wafer level tested, and there we sort the good number of chips, which is good one, and the backed chips are pointed using some inking technique, and those chips are not to be bonded or packaged. So that means our packaging machine must have a sorting unit which will sort the good one and reject the bad one. That is one condition the bonder assembly or bonding machine or assembly machine must have, and another is a pick up and place unit. The good one, how can judge the good one? The judgment is done from the visual observation on the wafer, whether a spot is given or some mark is given, some inking is given onto a chip. That is done during wafer level probing, wafer level testing of the chips. Now the correct piece of the chip, that means correct die, is to be sorted out and it has to be placed on the substrate material where it has to be bonded. So that means you have to have a pickup and place unit. A chip attach material station, supply station, and lead frame loader and unloader is also necessary. The major problem in chip bonding is the TC mismatch between the chip and the package medium. Temperature coefficient of expansion is a TCE. The TC mismatch causes stress because of thermal expansion coefficient. It causes stress during various stages, namely cooling the chip to room temperature after chip bonding, because chip bonding is done at a temperature 350 or 400 degrees centigrade. When you are bringing down the temperature to room temperature, then a cooling has to be done, and during that time a stress may develop if proper thermal matching of thermal expansion coefficient is not done. Next chance of stress formation is during wire bonding and encapsulation. Wire bonding, I mentioned that it is done using thermocompression, ball bonding or ultrasonic wire bonding. So there also the temperature of the chip increases, and when it cool down at room temperature, stress may develop. And third cause of stress is a burn-in soldering in the next packaging level. That means when you will fix up the package chip on a board or card, so to say, many chips are soldered there in that level, and there also you are heating the leads of the chip, and a high temperature will attain by the total package, and gradually it will bring down to room temperature, and there also there is a chance of stress formation. So that means in these three stages, one is during the chip bonding, second is during wire bonding, and third is during next package level. So in order to prevent the formation of thermal stress, proper matching of the thermal expansion coefficient of the wire bonding material and or chip bonding material and the package has to be looked into. Stresses cause chip cracking or chip delamination from the package medium, resulting in degraded thermal performance and reliability. If proper matching of TC is not there, there is a chance of formation of micro crack. At the same time, there is a chances of formation of delamination. So they will deteriorate the chip performance as well as they will deteriorate the reliability of the chip. In plastic packages, the stress combined with plastic moisture absorption might lead to package cracking rather than the chip cracking. These are the various considerations we have to look into before fixing up certain chip bonding process. Now I will discuss on solder die bonding technique. Chip bonding techniques began with gold silicon soldering for small scale integrated circuits, that is solder die bonding. Lead tin solders, which are also known as soft solders, were used later to bond MSI chips up to approximate 5 mm square because they were better stress buffer compared to hard solder. Hard solder is gold silicon solder, which were used earlier in SSI circuits, but it shows certain problems for stress matching, stress uh, elimination is to be there. So later on we shifted from gold silicon solder to the soft solder, which is a lead tin solder, and it were used for bonding MSI chips up to approximate 5 millimeter square. Recent VLSI chip bonding uses copper alloys that provide approximate 10 times the thermal conductivity of alloy 42. Alloy 42 is another solder material which is made using 42% nickel and 58% iron alloy. Alloy 42 were used for quite a considerable time for as a solder material for chip bonding, but later on when the copper alloy came into the market, then these materials are not used in that much, because copper alloys had certain advantages. It has got 10 times thermal conductivity, so that thermal stress will not generate there. So that is very important. That's why present VLSI chip uses copper alloys. Adoption of a copper alloy challenges the chip bonding technique to solve the TC mismatch problem. That means copper alloy also put challenges the chip bonding techniques to solve the TC mismatch problem. Now coming to the epoxy chip bonding. Silver filled epoxy adhesives are major choices as polymer based chip attach materials. These are silver filled epoxy adhesives are used, which are polymer based, and these polymer materials, in these polymer materials flakes of silvers are mixed, and to increase its thermal conductivity and electrical conductivity also. Silver flakes make the epoxy both electrically and thermally conductive. Silver filled epoxies are less expensive than gold content solders, which were used earlier in gold tin solders, and the silver filled epoxies are more flexible in absorbing the thermal stress. This is a very important criteria. Epoxy is fed onto the substrate material through a multi-nozzle dispenser. That is how to put the silver filled epoxy adhesives onto the substrate material. Epoxy provides better adhesion to natural silicon dioxide on back. That's why the epoxy chip bonding is preferred over earlier used the solder die chip bonding. Epoxy chip bonds do not need mechanical scrubbing, unlike eutectic chip bondings. Hence, there is a lower probability of damage to the chip edges in an epoxy chip bond. If you need mechanical scrubbing at the backside of the wafer, so there is a chance of formation of damage on the actual chip edges. As this epoxy chip bonding technique does not require this scrubbing, so it is better so far as damage formation is concerned compared to the eutectic chip bonding. As epoxies are thermosetting polymers, they must be cured at elevated temperature, and that temperature cycle is 125 to 175 degrees centigrade for 1 to 2 hours to complete the chip bond, because the epoxy chip is a thermosetting polymer. If you don't raise the temperature to that level, nearly 125 to 175 degrees centigrade, the complete bonding of the bonding of the chip with the substrate will not be done. If you elevate the temperature and you keep it for certain time, then only it bonds properly onto the substrate material. Automatic chip attach operation proceeds at a rate of 1 to 2 seconds per chip. After attaching the chip onto the substrate material, then you have to go for the curing, and you can cure the chips, large number of chips at the same time. So these are the salient features of the epoxy chip bonding technique. Now we will switch over to eutectic chip bonding. Eutectic chip bonding metallurgically attaches the chip to a substrate material, typically a metal lead frame made of alloy 42. Alloy 42, just now I mentioned in earlier slide, is a nickel and iron mixture, 42% nickel and 48% iron. And in this diagram we have shown how the chip bonding is done using the eutectic chip bonding technique. Here the substrate material is a ceramic or metal substrate on which we fix the chip, and for that purpose we first metallize the substrate, then we put the melting preform, which is basically the solder, and the chip backside is also metallized and it is put on the solder material, and the whole combination is heated at temperature 125 to 175 degrees centigrade for 1 to 2 hours. That means on the top side will be the active circuit, and below the chip it is metallized. This is metallization of the chip backside. This is a solder material, this is a melting preform, and here is the substrate. And the metallization, chip metallization and substrate metallization will help for proper alloying or proper bonding of the substrate and solder material with the chip. Backside of the chip is metallized. Here the backside of the chip is metallized to make it weightable by the chip bonding preform. That is also one of the purpose of metallizing backside of the chip. This metallization helps us to weight by the chip bonding preform. The features of the eutectic chip bonding are as follows. The preform which is used is a thin sheet of solder bonding alloy, and thickness of this preform is less than 0.05 millimeter, and its composition is 98% gold, 2% silicon. This is one eutectic material. Another is alloy or preform which we use is lead tin, that is 95% lead and 5% tin. So the gold silicon is known as hard solder and lead tin is known as soft solder. So they are used as a solder bonding material. Substrate material is metallized with plated silver or gold. At about 350 degrees centigrade, the preform reacts to dissolve the silicon. Preform is a solder bonding material, that is the preform that reacts, because here also you have 2% silicon. This alloy at 350 centigrade reacts and it dissolves certain silicon from the backside of the chip. The gold silicon eutectic composition is reached and then exceeded because the bonding temperature is set more than 400 degrees centigrade. As the composition of the composite structure becomes more silicon rich, it freezes and the chip bond is completed. This is the whole technique by which the chip is bonded onto substrate by using eutectic chip bonding technique. Now, after chip bonding is over, then we are coming to wire bonding. Wire bonding is the most common method for connecting the pads on the chip to choose on the package. Thin wire of diameter 25 micron to 40 micron is used. Materials either gold or aluminum. They are used for bonding the pads on the chip to those on the package. We use gold and aluminum wire because they bond well to pads onto the chip and to the lid. These form metallurgically stable connections. That's why we use either gold or aluminum, because they form metallurgically stable connections. Gold wire is ball and wedge bonded by thermosonics or thermocompression. Thermosonics means we use thermal energy as well as pressure energy, which is known as thermocompression bonding. And thermocompression is thermal energy and pressure, and thermosonic is thermal energy and ultrasonic energy. That is known as thermosonic bonding, and this is known as ball and wedge bonder. And in the next slides we will show you how this can be achieved using the thermocompression ball bonder, how a ball is formed and it is attached onto the bond pad. Then we shift it to the lid, package lid, and then there we form some wedge and cut the wire. Total sequence will be shown in a slide in detail. Now, the die temperature is maintained at 250 to 350 degrees centigrade. Aluminum wire is usually used for ultrasonic wedge bonding, but gold wire is used for ball and wedge bonded technique, wedge bonded technology there. Now, let us discuss little bit in detail of the ball and wedge bond technique. In this diagram, it is shown that this is a die and this is the bonding pad, one of the bonding pad. This is the bond head, nail head bond, and in this nail head bond there is a gap through which there is a channel through which wire comes, and this nail head is made of tungsten carbide, and this through this capillary the wire of 25 micron thickness diameter is coming. First, when the wire comes through this capillary gold wire, a ball is formed. With the ball formed on the end of the wire, the capillary targets the chip bond pad. This ball is formed with the help of a flame. So, by using a hydrogen flame, we melt the gold here and we form a ball, and this capillary is brought on top of the bond pads on a chip. Then the capillary descends, bringing this ball in contact with the chip. The capillary grips the ball in forming the bond like nail head. This is the nail head, you can say. So, after the ball is brought just under the die, now we put some pressure. With the pressure, a head is formed. This looks like nail head. Okay. After the nail is bonded onto the chip, the capillary rises. This is the capillary, the nail head, this is a bonding head rises, the clamp are open and the wire is free to feed out, forming a loop. The clamps means here on the top of the wire where the wire is coming, there was a clamp, and the clamps are open now, and the wire is free to feed through this capillary. Now if you move it, so that means you can see a loop here. So from the bond which is pressed on the bond pad, so a loop is formed, and then you are shifting the bond head on to the post. So this is the fourth sequence, and here the lead or post of the device is positioned under the capillary. So this loop is formed, then the post is brought under the capillary. This is the capillary. Now it deforms the wire by pressing against the lead, producing a wedge shaped bond. So here it deformed, you see it gives pressure, the capillary gives pressure on the wire. So there it deformed the wire like this. Here is the deformation. It deformed the wire by pressing against the lead, producing a wedge shaped bond. The capillary then rises. After deformation of the wire, the capillary, that means bond head, rises off the lead, and the wire is cut here using a hydrogen flame, and a new ball is formed for the next bond. So this is the total sequence of tailless bond and wedge bonding technique. So this particular technique is quite popular in wire bonding. Normally most of the cases we use this technique. The ultrasonic wedge bonder is not that much popular compared to the thermocompression ball and wedge bonding technique, because here the wire bonding reliability is much more compared to the ultrasonic wedge bonding. Now we will have a look on the second category of wire bonding, that is ultrasonic wire bonding, or it's also called the wedge bonding technique. Let's see here diagram. So there the steps are also shown. This is the die and this is the chip, and is the aluminum bonding pad on the chip. Die means small chip here. So this is aluminum bond pad. So here again this bond head, or say capillary, this capillary is brought down onto the bonding pad, which is made of aluminum. So then it puts some pressure on the wire using ultrasonic energy, using ultrasonic agitation. So here ultrasonic agitation and the pressure of the bond head. So there the wire deforms and it forms an wedge. Then the clamp releases and the capillary moves from the die. In the third sequence, the capillary moves from the die. So a loop is formed here, loop of wire is formed. It is taken away from the die, and in the fourth sequence this capillary is brought just above the post, or the capillary is brought in a certain position and the post is moved below the capillary. The capillary or the bond head is made of tungsten carbide. It's very hard. Then again, after bringing the post below the capillary, we put ultrasonic energy and pressure together to form a wedge on the wire on the post. After forming the wedge in this wire, then the capillary is taking up, it moves upwards. Okay, Now here is a wedge, then on post another wedge is formed, it is taken upward, then using a cutter we can separate the wire from this wedge shaped portion. So this is the shape of the cutter. So you can see here how it is cutting. So this is one piece, as another piece of metal. So they are pushed together so that here it is separated out. So in this way the wedge bonding is being done, and since here the energy used is ultrasonic energy, so it also called ultrasonic wire bonding. Now I will show you typical bonding pad sizes and spacings. So when you are going for packaging or assembly, so then you have to design the bonding pads on the wafer. That means what should be the minimum size of the bond pads, what should be the separation between one bond pad to other bond pad, what should be the gap between a bond pad and interconnection wires. So all these points has to keep in mind when somebody is designing a bond pad. And gap between one bond pad to other bond pad is also an important consideration. In this diagram we show you the minimum features, minimum gaps which are allowable for bond pad size and spacing. So here you can see in the diagram the bond pad size is 100 micron by 100 micron. This gap is 100 micron here, 100 micron by 100, and the wire diameter we are assuming 30 micron gold wire. Again, this is the interconnection line, for example. So the edge of the bond pad and the interconnection line spacing is nearly 30 micron minimum. Again, you can see here another set of bond pads are coming. So that bond pad to this bond pad gap is 60 micron minimum, and the wire to wire separation must be at least 120 micron minimum. And this is one sort of design. Another design is like this. This is so to say better bond pad design compared to this one. And here the length from this edge to this edge may vary. So this is total is 100 micron. So this gap may change is 50 or 30 micron, depends on design flexibility. These are the typical dimensions of tolerance between bond pad to bond pad and between the interconnection wires on the chip and the bond pads. So with this, let me stop now. And this is just now we discussed the wire bonding where we uses some wire. In the next lecture we will discuss on the beam lead techniques. In that case also we bond the bond pads with the post, that means beam leads, without using any wire, and those are known as beam lead technique. Those are most advanced techniques, and we will see how beam lead techniques are used for other VLSI package and assembly techniques.